So in today's class, we will be discussing about the elbow joint. So the elbow joint is a joint in the upper limb. Okay. So as I already discussed with you, that the joints in the upper limb offer you a large range of motion. So shoulder, we have discussed earlier, that gives you the largest range of motion. Then comes the elbow joint, which also is a complex joint and gives you a variety of motions or movements. Now, the elbow joint primarily consists of three bones: the humerus, radius, and ulna. Okay. So in this slide, if you see the anterior view from the front, and this is a right elbow. Okay. So you have the humerus, you have the ulna, and you have the radius. So if you look from the front, the radius will be located more towards the thumb. So if you just look from the front, the radius will be located laterally more towards the thumb finger. Okay. Now, if you are looking from the back, you can see that the radius is located on the lateral side and ulna towards the medial side. Okay. Now, if you consider this joint, elbow joint, it is basically made up of two joints based on the articulation of the bones. Now, the distal part of the humerus actually articulates with the ulna, forming the humero-ulnar joint. That is one joint. There is another joint, major joint, which is between the distal part of the humerus and the radius of radius. Now, these bones actually articulate through two different joints. So you can see the bony element trochila, okay, which is located at the end of the distal end of the humerus, and this trochila actually articulates with the trochlear notch of the ulna to form the humero-ulnar articulation. Okay. Similarly, the radius is articulating with the humerus through the capitulum. Okay, the capitulum is another bony landmark within the distal part of the humerus, and it forms the joint with the radius. You can see from the posterior side how these things look. Now, if I go to the next slide, a lateral view and a medial view, you can see the orientation of the joint. Now, it is very difficult to actually give you a clear idea how these things are articulating. It will be better if you refer to a YouTube lecture where these videos are actually uploaded, and it's very nicely presented lecture, which is called The Anatomy of the Elbow Joint, and the site is mentioned here. So I can mention this site again as I done it for elbow, for the shoulder as well. So the anatomy of the elbow joint, apart from what I have said, should be more clear to you if you watch this video in the YouTube. Okay? Now, I have actually supporting reading document that I will upload for all of you in the reading material section. And it has been written by a mechanical engineer, so it will be easy for you to conceive the whole structure, the relationship between the structure and movement. Now, we'll first take up the humero-ulnar articulation, as I told you, because that is a major joint that is responsible for the movement, flexion and extension. It is ideally a hinge joint, as you can see. So on the right, you have the trochila forming the joint with the ulna. And if you look from through the sagittal section, you can see that this trochila forms. This is how the joint is formed. This is the ulna. So it goes inside a notch, which is known as the trochlear notch. So the trochila is located on the distal part of the humerus and goes inside the trochlear notch of the ulna and forms the humero-ulnar joint or the humero-ulnar articulation. It is purely a hinge joint with a high degree of congruency, okay? And it offers you a large range of movement in the form of flexion and extension, okay? Now, if you look very carefully at the structure of the joint, you can see that the distal humerus is actually set anteriorly with respect to the humeral shaft. If you have the humeral axis or the humeral shaft of the humeral shaft, approximately it is set anteriorly at an angle of 40 degrees. Okay. Similarly, in the similar manner, the trochlear notch here, trochlear notch of the ulna is set superiorly and anteriorly at the same angle for congruency. Okay. So the angulation of the trochlear notch actually maintains the range of extension of the elbow to 180 degree before impact occurs between the olecranon process and the floor of the fossa. Okay, so there is a sort of stop where it actually the movement stops. So it is the range of extension of the elbow is up to 180 degrees. So we can summarize that it is basically a hinge joint. It is a major joint and it is a hinge joint. It offers movements only in form of flexion and extension. So you can flex your elbow and extend your elbow. So the articulation is between the trochila of the humerus and the trochlear notch of the ulna, and this joint has high degree of congruency. Now the next joint is the radiohumeral articulation. Okay. Now this articulation is between the spherically shaped capitulum, and the concave end face of the radial head. So there is a radial head which actually articulates with the spherical capitulum to give you the radiohumeral articulation. So what does it offer you in form of movements? It allows rotation of the radius at any angular position of elbow flexion. So even if you flex your elbow at any instantaneous position of a elbow flexion, you can rotate your arm inwards and you can rotate your forearm outwards, giving rise to the movements, pronation and supination. Okay, so this you can do at any angular flexion angle. Okay, so even if it is 180 degree sort of extension or it is some 90-degree flexion, you can always at that position this relative movement of angular movement inwards, pronation and outwards supination can be offered. However, as compared to the humeroulnar articulation, this joint lacks congruency. Okay, I hope you understand what is meant by pronation and supination. So pronation, supination are rotational movements. Inwards is pronation towards your body, and outwards to away from your body is basically supination. Okay, and you can see that this is quite a complex movement because it can actually, this movement can be obtained through a joint which is the radiohumeral joint. And if you look at the structure more carefully, it can be, you can observe it in the video that how this joint is formed more precisely and how the movements are executed. So the major muscles that are responsible for the movements. So as I told you, the major movements of this joint are flexion and extension. So we have the flexure muscles, mainly brachialis, biceps brachii, and brachioradialis. So these three muscles are the main flexure muscles in the elbow joint. Okay, so very roughly a sketch to give you, it's viewed from the medial side of the joint, and you can see clearly the muscles brachialis, biceps, long and short heads, and you have, why don't I see the brachioradialis? Yeah, I don't see the brachioradialis here in this view, maybe from another view. Then comes the extensor muscles. So flexion and extension are opposite movements. So you can see here that the triceps brachii is the main muscle that actually is responsible for the extension movements. Now, if I just superimpose another simpler picture, this is exactly what it stands, is that you have the triceps on the back of your forearm, and you have the biceps more in the front of your forearm. So when you are flexing your, should I say, the elbow, then the biceps are contracted, whereas the triceps are relaxed. But when you extend it, the biceps are relaxed and the contraction is in the triceps. Okay, so these are two opposite movements, and you can see clearly the contribution of the biceps and the triceps in each respective movement. Now, as I told you, the other two movements of the elbow, for which the radiohumeral joint is more responsible, are pronation and supination. Okay, so you have the muscles responsible for the pronation are the pronator quadratus and the pronator teres. So if I look little here in this picture you have these two muscles very clearly in blue. Okay, marked in blue are the pronator quadratus and pronator teres. So these are responsible for the pronation movement, that is movement towards the medial side of the body. Okay. On the other hand, the opposite movement, supination. Okay. Supination, you have again two main muscles. One is the biceps, you can see very clearly, and the supinator. Okay, they contribute towards the movement supination or rotation outwards. Okay, here you can see the brachioradialis muscle, as I was telling you. Okay, so if you see from the lateral side, the brachioradialis muscle would be visible, not from the medial side. Okay, so this is a sort of an overview that I've given between the structure and the function of the joints. What you actually can do is I'm going to upload this. Just give me a moment. I have this document, as I was telling you, from a book that is not available in the market anymore. Okay, so I have it with me, and I have scanned the relevant portion of the elbow joint. As you can see, some of the figures have been taken from this document. So if you read this document on the structure and movements, it's about 4 pages, and you can easily understand. This is the first part, which I have named elbow 1. So first part of the elbow joint. The second part is continuous, of course. You can get the page numbers. Starts from 88 page number of the book. But the book is not available. Okay, so I have it, a copy of it, I have it. So I have scanned it and tried to put forward as a reading material. So I will actually upload elbow 1 and elbow 2, which are continuous. In elbow 2, so the first part is more on the structure and function. The second part actually which is in fact continuous. So the second part starts from page 92, discusses about a problem, elaborate problem that I'm going to discuss in the class. Okay, so these two documents I will upload as reading material, and we need to discuss this problem, which is a very important problem as far as understanding of biomechanical analysis goes. So we have already discussed about in general biomechanical analysis, statics as well as dynamics, but this will be a problem on statics. We will discuss more about inverse dynamics if we consider the dynamic effect. But before that, discussing this problem is important in the class. Okay? So what I will do is now start discussion on this problem. But before that, I need to explain you the different aspects of the problem. Okay? So if I start discussion on this problem, then we will define the problem that the subject is carrying. The first important thing is the subject is carrying a sack of 50 kg weight. Okay? What is the position of the elbow? It is 90-degree flexed. So it is I'm carrying a weight, quite a weight of 50 kg. And the elbow is flexed at a 90-degree position. And you can see it is defined here. So if I like to highlight text, so this is exactly the position. So this situation puts a large load on the elbow joint, and the main flexure muscles acting to resist these external forces are the three muscles: biceps, brachialis, and brachioradialis, as I have already indicated in my earlier slides. So the flexure muscles, which are acting to resist these any external forces due to posture and carrying weight, are the biceps, brachialis, and the brachioradialis. Very, very important. Okay, and this is a sort of a diagram, a free body diagram of the elbow joint, where you can see that you have a joint axis A, and it is in a position of 90-degree elbow flexion. Okay, you have a wrist axis. So you have a wrist designated by two circles. So wrist and the elbow, wrist axis, joint axis, elbow joint axis. You have the applied load, which is 50 kg sack. Okay, you have the limb weight, of course. The limb has a weight. Now we have the muscles, action of the muscles. We have the biceps, we have the forces of the biceps, the forces applied by the brachialis, and the force applied by brachioradialis. So each is designated by FBI, FB small r, and FB capital R for representing the action of the muscles. Okay? And of course, you will give rise to joint reaction forces. So this, in a way, is a simplified, I call it simplified now. Why I call it simplified, you will understand later, because we are not considering the detail separation of the radius and ulnar together. We are considering it together now at this moment. Okay, so it is more a simplified free body diagram of the elbow joint carrying a load of 50 kg. So from geometry, which we can obtain from anatomy data, that the biceps, the action of the muscles, so the point of application and the line of action needs to be determined first. So these are the data of the bicep, brachialis, and brachioradialis. Insertion on the radius, you can see the data 0.038 meters. So with respect to the axis, joint axis A, so it is located at 0.038 is insertion on the radius. Brachialis is also 0.038 insertion on the ulna. There are two different insertion points. One is the radius, the other is the ulna. Okay, but at this moment we are considering the radius and ulna as one bone, forming a joint directly with the humerus. So limb weight is 0.16 meters, assumed point of center of the gravity. Okay, so the limb weight is located through the center of gravity of the limb. The brachioradialis is the muscle which is on the radius, so we have 0.24 meters far away from the joint axis, and the load 0.35 meters distal end of the metacarpal. So that is where the applied load is located. Okay, so based on this data, we can draw the free body diagram more precisely. Now, you need another set of data to define the line of action of these muscles. So we have point of application is the point of insertion, and you need the line of action. So in order to define the line of action, we have to define maybe another point through which the force vector passes. So this is the data 1, 2, 3, where the forces where we can define the line of action, based on which we can define the line of action. So we have the distance from the joint axis of the points. The action of the forces on the humerus can be defined using these locations, which is defined in the figure. So these forces, the muscle forces, are acting at different points, and it has different line of action. So obviously, there will be some moment arm of the respective muscle forces with respect to a joint center. Okay? So in order to determine the moment arm, we take the help of geometry and trigonometry, and we can easily find out the moment arm of the, say, brachialis muscle, denoted by LBR. Okay, so the moment arm is being, as I highlight, the moment arm of the brachialis muscle can be determined using geometry. Okay, similarly, we can determine the moment arm of the brachioradialis muscle, right? We can also determine the moment arm of the biceps muscles, muscle biceps. So individually, the moment arm with respect to the joint center can be determined using the geometry, the point of application, and line of action of the individual muscles. But why do we need this? Because we need to calculate the moment produced by this muscle. And these muscles are actually counteracting the effect of the weight that is being carried by the forearm, in a 90-degree flex position. So we have determined the moment arm, and you can just look into the calculations. From these figures 11.17, 11.18. Okay. Now there is an important assumption to proceed in the problem. Now we assume that the muscle tissue, the tissue of all muscles, are stressed at the same intensity. Okay. It's a muscle tissue, and there is an assumption that they are stressed at the same intensity. So there is a mean stress that is occurring or generated within the muscle. So if we assume sigma m as the mean stress produced in the muscle element, then the mean stress multiplied by the cross-sectional area, corresponding cross-sectional area of the muscle, or physiological cross-sectional area of the muscle, should give you a muscle force. Okay. Now, if you have anatomic data of physiological cross-sectional area of, say, biceps, brachialis, and brachioradialis, so the force exerted by the biceps should be the area of physiological cross-sectional area of the muscle, bicep, multiplied by the stress that is produced in the muscle. Okay. Thereafter, subsequently, the moment exerted by this force, muscle force, can be obtained by multiplying it further with the moment arm of the biceps. Okay. Individually, we can do for all the muscles. So force exerted by brachialis can be obtained. The moment produced by the brachialis multiplied by the moment arm, you can obtain. Similarly, for brachioradialis, physiological cross-sectional area multiplied by the mean stress multiplied by the moment arm should give you the moment of the muscle with respect to the joint center. Now, what is the external load now that we are trying to counteract through the action of this muscle? So the moment exerted by the external load or the applied load is the force multiplied by the distance from the axis. So we have what was given 50. The force is we have a limb weight, right? So we have 50.8 kg sac, and it is at a distance of, just let me check the data. The load is at a distance of 0.35 meters. Okay, so the load multiplied by the distance would give you a moment, the external moment of 87.2 Newton meters. Okay, if we consider the limb weight, say if we consider this 26 Newton as the limb weight, then multiplied by the distance of the CG of the limb with respect to the joint center, we get another additional moment of 4.16 Newton meter due to the limb weight. So the weight of the forearm is assumed to be 26 Newton, based on which we can calculate that the moment due to the limb weight is 4.16. So if we add 87.2 Newton meter and the limb weight moment, they will give you actually the total moment exerted by the external loads. Okay, so this is the moment produced by the external loads in form of applied load, the sac plus the limb weight. Okay, now as I told you earlier, the moments exerted by the individual muscles can be expressed in simple forms. So you have the mean stress in the muscle, the physiological cross-sectional area of the muscle, and the moment arm. So sigma m and A would give you the force, multiplied by the moment arm would give you the moment of the muscle force. Individually, you can do it for biceps, for brachioradialis, and you have the brachialis and the brachioradialis. Okay, so these three are the individual moments created by the muscles. So what we exactly do is now equate the moments created by the external force, that is 87.2 plus 4.16. So you can see here, so this is the moment, external moment, and this is the counteracting moment of the muscles that will counteract this external moment. So this is a very important equation to understand, similar to what I had discussed earlier in the class. Okay? If you recollect that when, say, we are in a standing posture, the joint reaction force passes through the joint center. The moment we actually, the instant when we move away from this static standing position to any other posture, the line of action of, or the force vector of the joint reaction force due to your body weight is not passing through the joint center, and there is an imbalance created by the moment arm. Okay, and that is counteracted by the action of the muscles. So exactly following the same principle, we are actually trying to calculate what would be the muscle forces for a particular instance, particular position of elbow flexion when we will be carrying a weight of 50 kg sac. So from this equation, we can easily determine the mean stress that is being generated in the muscles. So once we determine the mean stress in the muscle, multiplying with the physiological cross-sectional area of the muscle would give you different values of forces, magnitude of forces being sort of for each of these muscles. So we have, say, here the mean stress in the muscle, although it is same for all muscles, the forces applied by these muscles will vary from biceps because the physiological cross-sectional area of the muscle is different for different muscles. So we can calculate the brachialis force, the brachioradialis force, and of course the biceps. Okay, so I will stop here because this is the first simplified part of the problem. As we move down the problem, we will actually separate the joint later on. So we had started the problem assuming radius and ulna as one bone, and it forms a single joint with the humerus. Okay, a very simplified, idealistic way of starting the problem. Okay, then we will move on when we have two different joints formed by humero-ulnar articulation and humero-radial articulation. Okay, we will move more inside the problem in a more elaborate way, and then we will discuss it in the next class. Okay, for the time being, I stop here because it would not be wise to start another part and end abruptly. So if you have any question, I'm ready to discuss. Give me a moment to reorganize the meeting, and I have to stop recording.